This wind turbine harnesses a venerable mathematical concept, so remarkably effective that it stands as the initial apparatus to achieve near-perfect wind energy capture on a residential scale. This is the Archimedes wind turbine, generating less auditory disturbance during full operation than a hushed dialogue, posing no hazard to fauna, and in certain recorded installations, producing sufficient electricity to power a dwelling with over 90% annual energy independence. Yet, I wager you have never encountered one, nor are you likely to in the foreseeable future. So, what explains this peculiar situation? What renders this turbine so superior to a conventional one? And why has it not become the go-to solution for off-grid energy needs? To grasp the ingenuity of this device, we must journey back over 2 millennia. In the 3rd century before Christ, King Hero II of Syracuse commissioned a vessel named the Syracusia. Intended to be the most colossal ship of its era, its sheer magnitude presented an immediate challenge. A hull of such dimensions was prone to constant leakage, and expelling this water manually would have necessitated a crew size impractical for the ship to sustain. Consequently, the king sought the counsel of Archimedes, one of antiquity's most luminous intellects, to resolve this quandary. His solution was nothing short of brilliant. A helical blade encased within a cylinder, operable by a single individual, to displace prodigious volumes of water from the hull back into the sea. This identical apparatus found concurrent application in Egypt, where it was employed to elevate Nile water into irrigation channels, triumphing over gravity, to transform barren tracts into fertile agricultural land, and subsequently adopted by the Roman Empire for the dewatering of subterranean mineral excavations. For more than 2,000 years, the Archimedes screw remained the global benchmark for the most efficient means of fluid conveyance with minimal exertion. However, in 2003, a Dutch inventor named Miramat inverted Archimedes' foundational principle. Instead of a screw propelling a fluid, he posed the question, what if a fluid were to move the screw? Miramat had pinpointed a lacuna within Archimedes' preserved mathematical treatises. While Archimedes had delineated volumes for conventional geometric forms through their rotation around an axis, he had not explored the spatial potential of the three-dimensional helix as a rotor for energy transformation. Miramat's innovation involved reconfiguring the Archimedes screw into a conical spiral, meticulously engineered to engage with the turbulent, erratic, and direction-shifting winds typically found atop urban structures. The initial patent applications for this resultant design were submitted in 2006. Following a decade of practical trials, manufacturing commenced in South Korea in 2016, yielding what has come to be recognized as the Liam F1 turbine. However, to truly appreciate why the Liam F1 surpasses traditional bladed turbines for domestic applications, one must first comprehend the inherent limitations of conventional wind energy systems. Standard three-bladed turbines operate on the principle of lift, mirroring the mechanism of an airplane wing. They depend on a smooth, rapid flow of air across the surface of a slender blade to create a pressure disparity that induces rotation. This mechanism mandates consistent wind direction and sufficient velocity. Below approximately 9 to 11 miles per hour, most conventional turbines generate negligible power. Furthermore, when the wind's direction alters, the turbine's entire substantial mass must pivot, a process known as yawing, which consumes energy. And within the turbulent air layer found below 33 feet, above an urban rooftop, inconsistent speed and direction are precisely the prevailing conditions. The outcome is a turbine that vibrates, produces the characteristic rhythmic thumping that leads to noise complaints, and ultimately suffers mechanical failure without yielding any substantial usable power. The Archimedes turbine, however, rectifies these deficiencies through elegant geometry. Its rotor comprises 3 circular blades, spiraling around one another and expanding along a horizontal axis, forming a 3-dimensional conical helix that draws inspiration from the Fibonacci sequence and the natural geometry of the Nautilus shell. This construction generates a pressure gradient not across the thickness of a blade, but through the very spatial volume of the spiral. As wind enters the front of the turbine, its conical form compels the air to accelerate along the blade surfaces, reorienting the airflow by 90 degrees as it traverses the rotor and capturing a significant portion of its kinetic energy. This geometry bestows 3 mechanical advantages that conventional designs cannot replicate at a residential scale. The first is inherent self-orientation. Because the spiral is aerodynamically balanced, it aligns itself with the optimal wind direction without the need for electronic yaw mechanisms or sensors. In an environment where wind direction fluctuates every few seconds, this eliminates the energy expenditure and mechanical strain that incapacitate conventional turbines in urban settings. The second is broad directional tolerance. Despite being a horizontal axis turbine, the Archimedes design can capture wind approaching the rotor at angles up to 60 degrees from the axis. This renders it functional in the swirling, multi-directional air currents of an urban rooftop, where a conventional turbine would stall. And the third is a low initiation speed. The Liam F1 commences generating usable electricity at wind speeds as low as 5.6 miles per hour. Most conventional turbines of comparable size require 11 miles per hour of wind before they even begin producing a single watt. This theoretical design framework is substantiated by actual performance data. The manufacturer asserts that the Liam F1 achieves approximately 80% of the theoretical maximum power output permitted by the Betz limit, the physical law governing the proportion of wind's kinetic energy that any turbine can extract. While independent, peer-reviewed research and computational fluid dynamics simulations yield more conservative estimates, the design's efficiency remains approximately double that of conventional small-scale turbines. The most thorough independent evaluations were conducted by Pusan National University in South Korea at various sites, including the typhoon-prone coast of Incheon, where the turbine operated under conditions ranging from tranquil to extreme. The rotor demonstrated reliable self-starting at low wind speeds, stable operation in turbulent and directionally unpredictable airflow, and sustained no structural damage in circumstances that would incapacitate or destroy conventional residential turbines. In integrated hybrid systems combined with solar power, The Archimedes turbine has been proven to elevate annual energy self-sufficiency from 61% using solar alone to over 92%. This improvement was almost entirely realized during the autumn and winter months, when solar energy generation is typically lower. However, the advantages of this configuration extend beyond mere mechanical efficiency. Regarding acoustic pollution, the Liam F1 represents a substantial reduction. A conventional 1.5 kilowatt turbine generates up to 65 decibels during operation, characterized by the distinct rhythmic thumping produced by air being severed at the tip of each rotating blade. Conversely, because the Archimedes design lacks blade tips, the resulting noise level is less than 45 decibels at full operation, comparable to light rainfall and below the threshold of a normal conversation. The impact on wildlife is also noteworthy. Traditional three-bladed turbines rotate at high revolutions per minute, becoming a near-invisible blur that birds and bats cannot perceive as a solid impediment until it is too late. The Archimedes spiral, however, is a solid, three-dimensional form moving at a comparatively slow angular velocity. It does not dissolve into a blur. Instead, it remains a large, visible, slowly moving entity that wildlife can readily circumvent. Across more than a decade of field testing in environments spanning from the coasts of the Netherlands to South Korea, bird collisions with spiral turbines have been documented as virtually non-existent. Therefore, the Archimedes turbine stands as more efficient, quieter, and more robust than any other residential wind turbine presently available. So, why has it not become the standard for energy independence? The most evident answer to this question begins to surface when one examines the return on investment figures. A turbine of this nature typically incurs a cost in the vicinity of $5,000 to $7,000. At average urban wind speeds of 11 miles per hour, a Liam F1 system generates approximately 1,500 kilowatt-hours annually. Calculated at the current American electricity rate of 15 cents per kilowatt-hour, this equates to annual savings of approximately $225. This translates to a payback period exceeding 20 years. In high-wind coastal regions where the turbine produces considerably more energy, the payback period compresses to under 10 years. When contrasted with the average residential solar installation, which recoups its cost within 6 to 8 years, the choice is unequivocally clear for a homeowner making a financially driven energy investment. Naturally, there is more to consider than a simple financial calculation. As we have already observed, those seeking complete energy self-sufficiency and independence can utilize a hybrid system combining a Liam F1 with solar photovoltaic panels to establish an off-grid, year-round power supply. However, setting aside the initial expenditure, regulatory frameworks can present significant obstacles to the implementation of wind turbine technology in residential areas. Installing a turbine weighing between 220 and 617 pounds onto a residential roof necessitates structural engineering certification to confirm that the roof trusses can bear the load and the sustained vibrational stress without succumbing to fatigue failure, a process that is both lengthy and expensive. Homeowners associations can also pose challenges, frequently prohibiting wind turbines, citing aesthetic concerns, or anticipating complaints regarding noise and shadow flicker. And unlike solar energy, which benefits from solar access laws in several American states, small-scale residential wind power lacks equivalent legislative protection and is subject entirely to the discretion of local planning boards. Furthermore, the supply chain presents another impediment. Solar photovoltaics boast a well-established domestic installer network, standardized equipment, and clearly understood permitting processes in most jurisdictions. The Archimedes turbine possesses none of these advantages. There is no certified installer network in the United States. Most purchasers must arrange for do-it-yourself installations, which demand proficiency in three-phase alternating current electrical systems, maximum power point tracking, MPPT, wind charge controllers, dump load management, and roof structural assessments. Errors in any of these domains can result in equipment malfunction, voided warranties, or fire hazards due to unmanaged electrical surges. The absence of a professional installation pathway means that the technology primarily reaches technically adept early adopters rather than the broader residential consumer base. Nevertheless, for all those committed to integrating the Archimedes turbine into an off-grid or hybrid system, the initial step involves a wind assessment. The energy contained within wind is proportional to the cube of its velocity. A mere 20% difference in average wind speed results in a 72% variation in power output. Prior to any investment, an anemometer should be installed at the precise height and location designated for the planned turbine for a minimum duration of 3 to 6 months. The prerequisite for viable Archimedes turbine performance is a site average wind speed of 10 to 11 miles per hour. Below this threshold, the annual energy yield will not justify the capital investment within any reasonable time frame. Above it, particularly in coastal or elevated rural locations, the economic viability becomes substantially more favorable. The turbine must be positioned at least 10 to 16 feet above the highest point of the roof or any nearby obstruction to escape the boundary layer of slow, turbulent air that forms around built structures. A turbine mounted at an insufficient height within the turbulent zone directly above a roofline will generate a fraction of its rated output, irrespective of the regional wind resource. Regarding the structure itself, the Liam F1 is the primary commercially available product, typically priced between $5,000 and $7,000, inclusive of the controller and mounting hardware. A smaller model, the AWM 750D, capable of producing a maximum of 150 watts, is available at a reduced cost for battery charging in off-grid cabin scenarios. It is advisable to steer clear of low-cost spiral turbine imitations found on mass-market online retailers. These are generally plastic units equipped with undersized generators that fail within months and bear no resemblance to the decade of aerodynamic development that underpins the documented functionality of the genuine Archimedes design. The electrical integration also necessitates careful consideration and the procurement of specific components. A wind-specific MPPT charge controller is essential for managing variable input and preventing overspeeding. A dump load, comprising a bank of resistors capable of dissipating excess energy as heat, is also mandatory. When batteries reach their full capacity, the dump load prevents the turbine from rotating without a load, which could cause it to accelerate beyond its structural limits. For energy storage, lithium iron phosphate batteries are the preferred medium for wind systems. They adeptly handle the inconsistent pulsed charging profile of a wind turbine, outperforming lead-acid alternatives, and a battery management system is required to shield the cells from high-voltage surges during gusts. Ultimately, these turbines perform most effectively as an integral component of a hybrid system, rather than as a standalone energy source. Solar photovoltaic systems achieve peak generation during summer daylight hours, whereas Archimedes turbines excel during winter and at night. These two generation profiles are complementary rather than competitive. A 1.5 kilowatt Archimedes turbine coupled with a standard solar array creates a generation profile that approaches continuous round-the-clock production across all seasons. As for upkeep, the requirements are fairly minimal. Bearings should be inspected annually. Blades ought to be examined for accumulated debris or ice formation, which can unbalance the rotor. The braking system, incorporating an electrical brake managed by the controller and a mechanical backup, should be tested annually to confirm operational readiness. The Archimedes wind turbine applies a 2,000-year-old geometric principle to generate usable power from wind in the most efficient manner currently achievable. Much of what this channel explores functions precisely as advertised, costs less than its replacements, and was set aside not due to failure, but because the prevailing system was never designed to accommodate it. If such aspects resonate with you, subscribing and sharing is the most straightforward method to ensure its continued discovery. And if you wish to learn how a French forester managed to power his residence and vehicle using nothing more than a heap of decaying branches, that video is presented next.